Hello and welcome to the wolfSSL live webinar, Linux Kernel Module with FIPS140-3, presented by wolfSSL Senior Software Engineer Daniel Pouzzner. My name is Shizuka and I will be moderating this webinar. All attendees will be in listen-only mode. If you have a question, please use the Q&A box. We will host a Q&A session following the presentation. The webinar will also be recorded and made available on our YouTube channel shortly after the presentation. If you'd like to stay updated with all the latest from wolfSSL, follow us on X, connect with us on LinkedIn, and subscribe to our YouTube channel. Also, feel free to email us at fax@wolfSSL.com if you have any additional questions. And now, I would like to give a brief company overview before we move to the technical presentation. Today, wolfSSL secure over 2 billion connections. We have more than 1,000 OEM customers and dozens of resellers. wolfSSL is made up of over 50 dedicated employees, most of which are engineers. This progress is of course supported by a strong partner network that we are proud of. Since the beginning, our engineering team has developed several embedded security products, including WolfCrypt with DO-178 support, FIPS certification, and a FIPS-ready offering, MQTT up to the V5 specification, SSH v2, TPM 2.0, a secure bootloader known as WolfBoot, Java wrappers, and a JSSE support, commercial support for Coral, and our latest product offering, wolfHSM. These offerings are accompanied by through maintenance and support plans up to the 24/7 level. We also offer full service consulting. And now I would like to turn it over to Daniel to talk about Linux Kernel Module with FIPS140-3.
Thank you, Shizuka. All right, so what we're going to talk about today is wolfSSL's Linux Kernel Module offering. This is, I think, the third time we presented this webinar, and we're going to start with a lot of updates. So if you've attended this webinar before, you'll get the news first. The first thing that I'll point out is that on our cover page here, the name of the module that I've given is libwolfssl.ko.signed. Now, the sign, the module signature mechanism has been in the tooling for our kernel module build from the start. But when you're doing a FIPS build of your kernel at the Linux configuration level, it has to be signed. So you'll need to use the signed version in order to get it to load in the first place. So this is the same slide that we've always had in our kernel module presentation. The kernel module is actually a port of our entire library. The library itself consists of two parts: wolfCrypt, the underlying cryptographic implementations of all of the algorithms and the basic ASN parsing, and then layered on that is the TLS and DTLS layer. Now, we're very much focused on the wolfCrypt side in terms of the delivered functionalities and our testing program for the kernel module right now. Eventually, we will, of course, move into further support for the TLS layer. But for now, we're really focused on the crypto layer. So today, we're going to try to focus a little bit more than in previous versions of this webinar on the FIPS140-3 aspects of, and we've talked about this before, but we'll focus on it more because we've made a lot of progress on the FIPS140-3 support. The entire suite is now fully supported in kernel mode, but more importantly, the entire suite is supported with the AES-NI and AVX accelerations enabled. And that means that our FIPS140-3 performance in the kernel module now matches or exceeds the performance of the in-tree implementations of those same algorithms. And just to back up for a second, the big reason that you're interested in using the wolfSSL library or wolfCrypt in order to meet a FIPS140-3 requirement is that you are not bound to any particular Linux kernel major version when you use wolfSSL or wolfSSL.ko.signed as your FIPS140-3 crypto provider. We support kernels from the 3.x series all the way through the latest release candidate and every LTS kernel in between. I'll talk a little bit more about that later, but that's the big advantage. Well, one of the big advantages here beyond our much higher level of support for these functionalities. It's that you can decouple your FIPS140-3 requirement from the version of the Linux kernel that you're using, and updating your kernel version becomes just a matter of getting a new operating environment certification within an existing certificate. So that's very convenient. I mentioned this at the outset that when you do config crypto FIPS on your Linux kernel now, our kernel module is completely compatible with that mode. So one of our marquee use cases for FIPS wolfSSL cryptography in the kernel is that we now have turnkey support for FIPS140-3 AES-XTS in the kernel. This is a no-code capability. You build the library or the module with appropriate arguments, and when you load that module, it installs itself as the highest priority provider for the AES-XTS algorithms. And then when you mount or operate on an encrypted file of one of the LUX file systems, that's the usual entryway of doing encrypted file systems, performant encrypted, modern encrypted file systems on Linux, it will automatically be, the cryptography will automatically be fulfilled by the wolfSSL implementation with full FIPS certification and startup self-test. So that's probably one of the biggest takeaways today, is that you can meet FIPS requirements with a no-code option for disk encryption using the wolfSSL kernel module today. This is an old slide, but it's still current. The performance that you see in kernel is very similar to the performance that you see in user space. So if you're wondering what sort of performance you'll see for a particular algorithm, you can just run the wolfSSL user space benchmark and get a good sense of it. That said, we've also ported our benchmark application to the kernel, and you can run and this is not something to do in production, obviously, because benchmarking is both fidgety and disruptive to the system. But when you want to get ground truth on what your performance will be using the wolfcrypt implementation of an algorithm, you can now get that by running the benchmark inside the kernel. And that's just achieved using an option, enable Linux KM benchmark. And it will just actually run, when the module loads, it will run the benchmarks in the kernel and print out the empirically measured results, which can resolve a lot of mystery about exactly what you'll be looking at when you migrate to wolfcrypt as your solution for a cryptographic requirement. Another thing we are very excited about is that we now have a fairly extensive suite of native quantum-resistant cryptography algorithms. You can see them called out here. We have Kyber, dilithium, LMS, and XMSS. Those are all kernel compatible. They run inside the kernel module. The self-test routines run inside the kernel module. And soon we will actually be adding the x86 accelerated versions of these that leverage AVX and other assembly optimizations. And then we will have fully performant quantum-resistant cryptography available inside the kernel to any other kernel modules that want to use them. There is no quantum-resistant cryptography in the in-tree Linux kernel yet. So this is a way that you can get access to quantum-resistant algorithms today in the kernel. And the main branch, the master branch of wolfSSL, has these capabilities ready to use today. So if you're eager to try it out, you can clone our repo today, build it, load it, and start playing with it. And it already works. So I want to talk in some detail. FIPS140-3 is largely a compliance and testing story. So I want to talk more than I have before about the breadth and depth of our testing program that is specific to the kernel module. As many of you will probably already be aware, wolfSSL has a very extensive testing program on the library on many different targets. We test on more than half a dozen silicon architectures in our routine testing. We use a long list of static analyzers on every piece of code that merges, and we have even more extensive testing, including proprietary static and dynamic analysis and our nightly testing. So we are the best tested cryptography in the industry, and now I'm going to explain how we are the best tested kernel cryptography in the industry also. So the first thing is that we test on a huge variety of kernel versions, and we test with multiple compilers. We also test many different kernel configurations. This is something that it's dangerous to take for granted that your kernel code will work in all of the possible configurations of the kernel, because some of the kernel configuration options change the code that gets gated in quite dramatically. Symbols will turn into macros, macros will turn into symbols. There will be multiple layers of shims from various options, and extra restrictions or relaxed restrictions. And the only way to find out if it works right is to test it. So that's what we do. And then, speaking of actually testing it, we do actually boot these kernels, this huge long list of about a dozen kernel versions under QEMU system. And then we actually load the module, and then we use scripting using a program called expect in order to fully exercise the cryptographic capabilities and filter the output from the kernel log for anything that isn't just right. So the first thing I said I would talk more about this, and now I will. Our kernel version coverage is quite extensive. We now support or test on every LTS kernel going as far back as 4.4 through 6.6, the most recent LTS kernel. And we also, just for completeness, we do test on 3.16, a 3.16, which is 10 years ago. So we're testing a decade worth of kernel versions. And we do that because we want to make certain that anything that ever works with either libwolfSSL generally, or it's the kernel module specifically, will continue to work essentially forever. It's not hard for us to test on all this old stuff. We have gated conditions in the codes that allow us to accommodate the idiosyncrasies of these older versions alongside the idiosyncrasies of the newer versions. And I'll talk about some of those idiosyncrasies soon. And the last thing that I want to call out here is that we do test on the very latest release candidate of Linux also, which allows us to catch any breaking changes in the upstream Linux kernel and merge the fixes for them before that Linux kernel is even released. And what that means is that any released Linux kernel version is supported by the wolfSSL kernel module, and that is essentially true at any time. It's a negative delay between breaking changes and a fix for those breaking changes in the master branch of wolfSSL. And then the subsequent release of wolfSSL includes those fixes. So I talked a little bit about the need to cover different kernel configurations. Here's some of the highlights of kernel configuration options that we exercise extensively. So the Crypto Manager, this is the self-test framework for cryptography. And when you enable that, the kernel uses a set of compiled-in test vectors and a wide variety of calling scenarios to exercise the cryptographic implementation that you're loading and confirm that everything is as expected. And if it's not as expected, then the kernel module load is actually rejected, which is exactly what you want, of course. You can't have a defective cryptographic implementation being loaded because it will corrupt data. So we use that in order to vet our implementations, to make certain that we are bit perfect on every scenario, that we have completely replicated the expected semantics of the Linux kernel. which sometimes are have wrinkles in them. Sometimes they are non-standard, and we do replicate any non-standard semantics expected by the Linux kernel to assure perfect compatibility, drop-in compatibility with the Linux kernel. The second option you see here, the extra tests, that is a built-in fuzz tester. And we run thousands of fuzz tester scenarios every night on various build options of wolfSSL to make certain that we are matching with and without assembly, with and without fortify, and various other scenarios, that we perfectly match all of the expectations when fuzzing the cryptographic implementation. So that clearly builds a lot of confidence in the comprehensive correctness of our implementations. We also use the built-in sanitizer capabilities of the Linux kernel, both for undefined behavior and for addresses. Obviously, we use all of the sanitizers both under GCC and under Clang in user mode in order to, and in a vast variety of configurations in order to confirm correctness in our implementation. But there is still no substitute for confirming correct dynamics in the exact target you're going to be running in. And that will sometimes tease out edge cases, alignment failures, things that are unique to the exact compilation options from the K-build framework. So we do that every night, and that also builds confidence that our implementation is comprehensively correct. We also do memory leak analysis that is actually occasionally able to uncover memory leaks at the edges that aren't picked up by Valgrind or the sanitizers in user mode. So a lot of the analysis that we're doing that's focused on the kernel module actually helps our quality assurance in the wider product, because it catches coding errors that for one reason or another aren't caught by the other analyzers. And you can never have too many analyzers is really the takeaway from that. Another option that we test with and without is fortify source. There are assumptions that the kernel fortify source option makes about the way you're using certain keywords and such that we have to accommodate. So we make certain that we are fully compatible with fortify source. Another option that's very useful for us is x86 debug FPU. That's an option that causes the kernel to verify with every return to user mode that there have been no alterations to the floating point registers that were not properly saved and restored by the kernel code. And we use we actually use the vector registers, not the floating point registers, but this is debugging the vector registers and the floating point registers. And we use them extensively for AES-NI and AVX accelerations. So using this option allows us to have complete confidence that we have properly saved and restored all of the floating point and vector registers exactly as we need to. As I noted earlier, we are now fully compatible in testing with crypto FIPS, which actually connects with the dynamics of the crypto manager, because it turns out that certain scenarios that are tested in a non-FIPS build of the Linux kernel are forbidden in FIPS. Short keys are an example of that. There are scenarios in the non-FIPS crypto manager workout using short initialization vectors, short keys, duplicate keys. And AES-XTS is another example of a forbidden scenario, a FIPS forbidden scenario that is exercised in a non-FIPS build. So in fact, to test our FIPS build of our kernel module, we have to build the kernel with the FIPS flag so that the crypto manager expects failure rather than success on the FIPS forbidden scenarios, which is exactly how it works now. And the last one here is module sig all. That just makes certain that we're properly signing and verifying the module signatures on all of the modules, including the wolfSSL module. So as I mentioned in the overview slide on our testing program, we exercise all of these capabilities with and with QEMU system, a system emulator, we actually boot the kernels, and we use in kernel mode, we run the wolfcrypt test routine with all of the algorithms enabled. As I said, we can optionally also run the benchmarks, which is that's a testing thing to do. And we do test the benchmark functionality in our nightly testing. We also do a fully scripted workout from user mode of the kernel cryptographic capabilities that we install on the kernel side using libwolfSSL.ko. So that, and we do full interoperability testing to make certain that a file system that is created using an AES-XTS encrypted file system that's created with the in-tree cryptography can be accessed with bit-for-bit perfect compatibility using wolfcrypt and vice versa. You can switch back and forth between them. That is what we do in our nightly testing program, is we switch back and forth between them and confirm that they are bitwise identical, regardless of which cryptographic implementation is being used on the backside. And as I mentioned, we also comprehensively screen the output from the emulator. It's the kernel log. We screen the kernel log using a carefully collected set of patterns for any errors or warnings that we don't expect to see. Obviously, the boot sequence itself before the module loads has various meaningless warnings in it, as all boot sequences will display. We ignore those. So now I'll talk a little bit about how the wolfSSL kernel module came to be in the first place. If you've seen earlier versions of this webinar, some of this will be familiar, but it is updated for the latest nuances of the way we're solving the problems that we run into. So here's another overview slide. The main objective with the kernel module port is to make it as clean and easy to maintain and keep in sync with upstream with the latest Linux kernel as possible. And the most important way to do that is to make certain that you are leveraging the Linux native kbuild toolchain to maximum potential, which is exactly what we do. So you configure for the kernel module using this simple switch here, enable Linux KM. When you do that and run make actually just hands control of the make process over to kbuild, and then kbuild does the actual compilations, and it does so using the compilations, the compiler switches, the linker options, all of the configuration that the kernel, that particular version of the kernel, has selected. And some of those options are actually a function of your kernel configuration. So when you update your kernel configuration, it will be reflected in the build of the wolfSSL kernel module. There's no extra work to do. It all just works. And we make certain that it just works because, as I said earlier, we test on a huge variety of kernels, and going all the way back to the 3.x series and all the way up to the latest release candidate within hours or days of the release of that candidate. And the source tree is unified. There are a few kernel module specific pieces that are in the Linux KM subdirectory of the repository, but there's no replication of code. All of the source code for the cryptographic implementations in the kernel module are the regular implementations that are also used for user mode builds and for embedded builds for other embedded targets. So the big challenge with a kernel module port, just like any port to a deeply embedded environment, is that it's not POSIX at all. And the hill is even steeper with kernel mode on Linux or BSD or Windows than it is with a lot of deeply embedded environments like FreeRTOS, because you have a tiny stack and you can't change the size of it. You're stuck with 16K or occasionally even 8 kilobytes of stack total, and there's nothing you can do about it. It's a system-wide constraint, and you just have to live within it. There's no C library. There's the kernel library that has calls that look like C calls like, mem copy and whatnot. Those exist, but they're not from the C library. They're from the kernel library. There's no stack red zone, so you can't use a few bytes of stack early the way you can in user mode. There's certainly no thread local storage. There can't be. I'll talk more about that in a later slide, but thread local storage is essentially a contradiction in terms in kernel mode, because kernel mode has run contexts that aren't associated with a thread, either a kernel thread or a user thread. You started to hear a little bit about the awkwardness of using the vector registers in kernel mode when I was talking about the debugging option in order to make certain that we have all of our save and restore buttoned up with the vector registers. But that's a very unusual requirement. In user mode, you never have to think about that. You never have to think, oh, what CPU registers do I need to save here and restore later, or the inverse of that. Because it's all taken care of for you by the operating system. But here, when you're a kernel module, you are the operating system, and that responsibility falls on you, because one of the optimizations in kernel mode, and this goes not just for Linux, but also for BSD and for Windows, is that the kernel will not implicitly save and restore your vector registers for you. It will do that for your integer registers, sure, because all code has to use integer registers. But the assumption is that most kernel code won't touch the floating point and vector registers, and consequently, it would be a waste of effort to read out those hundreds of bytes of vector and floating point registers to save them to a buffer in memory and then restore them when you return to user mode, because they're not going to be touched anyway. But we do use them for the cryptographic acceleration. So we have to take care of that, and the kernel does provide facilities that let us do that. This isn't really a problem, although it is a bit of a treadmill. The Linux code base dates back over 30 years. And what that means is that there's a lot of code patterns in the Linux kernel and in its headers that are not modern. And when you turn on the types of warnings that modern code is expected to be clean on, the kernel will not be clean on them. The way we accommodate this is that we suppress only the warnings that the kernel headers are not yet cleaned up to be clean on, and we suppress them only as long as we are including kernel headers. And then we restore our usual set of, all of the warnings. That we turn on practically every warning in the compiler to make certain that our own code base is as close as we can get to perfectly clean. And that's even with the pedantic flag. A more substantive obstacle to keeping things clean and functioning correctly and building successfully on the Linux kernel is that the Linux kernel is very much a moving target. So as I mentioned earlier, we have a lot of gating in the glue logic for the kernel mode build that's specific to versions or version spans within the Linux kernel, because the way you do a given thing, the way you solve a given problem in the Linux kernel changes from year to year. And it's not just stuff down in the weeds that changes. Here's some examples of the type of thing. In 5.15, the kernel equivalent of printf, its name changed to _printk from printk. It had been printk for 25 years, and suddenly it was _printk. In 6.4, this module, which for a kernel module is that's how you get access to the parameters of your module, like where it is in memory, where its different segments are located in kernel memory. It was completely reorganized. So our code that we were using in order to sanity check the locations of the module in memory, which is related to FIPS, and I'll talk more about that later, we had to add in version-specific code to work around the new way of doing that. And that's par for the course. The latest release candidate, 6.10, malloc itself is shemmed with some compilation options. 6.10 introduces something quite nice, actually, which is very low overhead memory leak analysis. We're not using that feature yet. We're still using the legacy KMEM leak functionality, but sometime this year after 6.10 is released, we will probably add in leveraging of this new entry capability in the Linux kernel. KMEM leak turns out to be fairly burdensome. And if we turn on both the KMEM leak and the kernel sanitizers at the same time, we find that running that kernel under QEMU's system is prohibitively slow. We're talking like 3 to 4 minute boot sequences and the like. So that's not an attractive option. And then another thing that 6.10 is bringing into the Linux kernel, which is probably going to impact quite a few out-of-tree kernel modules, is that one of the contributors did a search and replace operation so that the src variable in makefile.build was renamed to obj. Entry builds aren't affected by this because obj and src always have the same value entry. But if you are supplying an override value for src, that build strategy is no longer viable with when 6.10 is released. We worked around that by creating a tree of symbolic links so that we can now compile with obj and src having the same value. And previously, we could make them be separate values so that we could point src at the parent main. As I said earlier, the cryptographic implementations, the main source code for the kernel module is the same as for the regular library. So we were just pointing src at our main source tree. And we don't have that option any longer with 6.10. So I'm going to quickly run through some of the nuts and bolts challenges that we ran into doing this port. It is a very small stack in the kernel, and you can't make it any bigger. So we had to expand the coverage of our small stack build option, which you can do enable small stack if it's an auto tools build, or you can just define wolfSSL small stack if you're using user settings.h, our embedded oriented configuration strategy. That now has comprehensive coverage. So this was a prerequisite for fully supporting kernel mode for wolfcrypt and the TLS layer alike. The stack, we can never tax the stack beyond around 8K. And for the most part, we don't even get close to that. The requirement that stack usage be formally controlled obviously also requires elimination of all recursive functions. So we refactored several functions to eliminate recursion. Our general rule is that we have a test procedure that allows us to confirm with every commit to the repository that we are never putting any big num data, any multi-precision integer data on the stack in a small stack build. And that means that the key size choice for multi-precision, let's say you have a use case where you need to support 16 kilobit RSA keys, which requires at least 32 kilobits of big num state being stored at any given time in the implementation of support for that RSA key size. That never goes on the stack. So, and that is in fact the way we test to make certain that we'll never do it, is that we set the build options to support 16 kilobit RSA, and then we look for any stacks that are that size or bigger, any stack frames that are that size or bigger, and we therefore never have any occurrence of that in the code base. Here's some examples of the type of stack usage that you'll see. These are pessimistic numbers. The actual stack usage you'll see in practice if you call into wolfcrypt from your own kernel module or elsewhere in the entry kernel is smaller than these, because these figures reflect the stack overhead from our tests. And our tests, they're not stack usage abusive, but they're also not stack usage optimal. They're intended to be good enough to correctly test the code against compiled in test vectors, but it's not fully optimized for stack usage the way kernel code is. So I talked earlier about the leveraging of the K-build environment. One of the requirements in the kernel is that you have to export all public implementations using a kernel-specific macro. And obviously, wolfSSL has to do that too. And the way we actually do that is that we build the module in the usual way, creating the link.o, and then we use ELF tools in order to examine which symbols in it are marked using ELF annotations as exported public symbols. And then we automatically build a file with a concatenation of all of those macro invocations needed to export them using the kernel method of exporting them. So that's how that works. And that allows us to simultaneously leverage the kernel tooling and the wolfSSL tooling in a essentially, it has there's a zero maintenance aspect to it. And that's exactly the type of thing that we think protects our customers from any possibility of any sort of obsolescence. This stuff is largely self-maintaining. So now I'll talk in a little bit more detail about the challenges of targeting the wolfSSL kernel module for FIPS140-3. So the main challenge here is that this runtime model is not anticipated by the kernel module loader. The kernel module loader rewrites various internal aspects of the module when it is loaded. And that means that you have to load the module carefully in a way that does not lead the linker to disrupt the bit pattern in the module. Because in FIPS 140, both 140-2 and 140-3, the in-memory signature, the bit pattern in memory must be stable. When our module is loaded, this is true in both user mode and in kernel mode. When our module loads, it checks itself by running a SHA-256 HMAC across the entire span, the entire text span, which is the function implementations, and read-only data span, which is the compiled-in constants. And the resulting SHA-256 HMAC hash value has to match a compiled-in correct value. And that, in turn, guarantees that it is bitwise identical to what is expected, and therefore that the code that is going to be run at runtime is guaranteed intact and correct, given that there's the original implementation from which it was built and from which that SHA-256 HMAC was generated was subjected to comprehensive laboratory examination. And this is our way of squaring that circle, is that we use the position independent executable mode of compilation, which sounds like a contradiction in terms because it's in kernel mode, but it is in fact the only compilation mode available in unmodified GCC that will allow you to create a fully relocatable and therefore fully stable version of the kernel module for loading at runtime. I mentioned earlier that there is no thread local storage in the kernel. The way we implement FIPS self-test dynamics uses, in user space, uses thread local storage. We just use intrinsic atomic operations to achieve a similar result in kernel mode. And I already talked extensively about this, so we don't need to talk about this in detail. But we do have to very carefully accommodate the proper saving and restoration requirements for the vector registers to make certain that we are not corrupting user state. And we use the kernel's debugging capability around that, in addition to our own internal debugging aids optional debugging aids to confirm comprehensive coverage around that. Another requirement that we meet with custom logic is a recursable, a nestable save restore dynamic. We do that using a lock-free per CPU buffer. So that's essentially zero overhead. And that's one of the reasons that the kernel mode performance is essentially identical to the user mode performance. We use a very cheap logic in order to meet these requirements, computationally cheap logic to meet these requirements in the kernel. One of the proof of concepts that we did years ago for the kernel mode build of the wolfSSL library is WireGuard. So WireGuard is it's a Linux native VPN. It's a very lean and mean native implementation of VPNs. It has a user side and a kernel side, as do all VPNs. We replicated all of the cryptographic logic and put a set of shims together that allow wolfcrypt to fulfill all of the cryptographic requirements. And in fact, we implemented the XChaCha symmetric cipher specifically to support WireGuard. WireGuard could be re-implemented using FIPS algorithms. It's something that we've thought about. We haven't done it, but the advantage with re-implementing using FIPS algorithms is that actually winds up bringing in hardware acceleration that isn't available for ChaCha or for Blake, the hashing algorithm that WireGuard uses natively. So that's an interesting thing that we may look at in the future. So speaking of future directions, eventually we're going to get more serious about the TLS side in kernel. We're going to add in both example code and a testing program for TLS endpoints that terminate inside the kernel. There's various use cases for that, and they're interesting. Hasn't been our focus yet, but in principle, we do already support it. I would have some misgivings about stack usage. You'd need to look very carefully on a case-by-case basis to see if things work for you in your use case as they stand, and we'd be happy to help out with that integration process. We do already support other targets with the C build of our cryptographic implementations, but currently we're only supporting the x86 assembly accelerations. We support them for the entire FIPS140-3 cryptographic suite. So all of the SHA algorithms, SHA-2, SHA-3, Shake, all the ECC curves, all of the AES modes, those are all fully supported with AES-NI and AVX accelerations in kernel mode. So you get essentially the same performance in kernel as you get in user mode for those, but that's currently only on x86. So the exciting development for the future is bringing in the ARM, the corresponding accelerations for ARM. And that will probably happen this calendar year. And all integration of accelerated code is all a case-by-case proposition. Sometimes the code works the first time we try it. Sometimes there's a few adjustments that we need to make just because of the special requirements of running in kernel mode. Another thing that we would like to add, especially to support post-quantum use cases, is TPM support, because TPM HSM is fundamental to fully supporting post-quantum cryptography, and we want to do that, and we want to do that in kernel mode. And we have made a very strong start on post-quantum support in kernel mode, But for FIPS compliance purposes, when FIPS crosses that bridge and the quantum resistant algorithms are added to this suite, some of those algorithms in signature mode in particular require running in an HSM and a TPM in a fully protected runtime environment. And we want to be able to support that on day one. And with that, I await your questions.
Thank you, Daniel. There's a question, how portable is the kernel module built?
So portability has always been a focus both of wolfSSL generally and of the kernel module. And because we're leveraging the K-build toolchain, if you're doing a C build of wolfSSL, it will essentially work out of the box on any target supported by Linux, currently supported by Linux. That said, if your target is 32-bit and doesn't support a 64-bit type, some adjustments might need to be made. But if 64-bit integers are supported, it will work right out of the box. The assembly acceleration story, as I said, is more restricted. Currently, that's only known to work correctly on x86, but AArch64 ARM accelerations are coming soon and will be similarly comprehensive. They will span the entire FIPS140-3 crypto suite.
There's a question, does this work on ARM?
Yes, it does. We've had customers that have targeted the build at ARM CPUs. We've also had customers target MIPS. In fact, we've had a customer target 32-bit MIPS. And with some slight modifications, that did work. So yeah, as I said, anything that current Linux can target, our kernel module can target. And we're supporting and testing on kernel versions all the way back to, I think it was 3.16. 3.16 is the oldest kernel that we support.
There's another question, how does performance compare with the built-in implementations in Linux?
Oh, that's a good question. So the so on AES-XTS, for example, which is that's a real apples to apples comparison because we currently support installation of AES-XTS as the highest priority crypto provider in the Linux kernel crypto system API. Where we seem to be 2 to 3% faster, but I think you should just treat it as a parity, performance parity with the fastest assembly accelerated in-tree implementation of AES-XTS. So like on a decently performant CPU, you'll see that like 3.5, 4 gigabytes a second on a per core on AES-XTS. And that, yeah, it's similar with the other implementations because our accelerated assembly on x86 is at or exceeds any implementation in the industry where we are best in class. Actually, just typically we're the fastest, period. And we maintain that performance advantage running inside the kernel.
Okay, they have another question. Does the kernel build have any dependencies?
No special dependency. I mean, you have to have a kernel that's configured. Beyond that, if you could, the upshot is that if you can build a kernel, then you can build this kernel module. It doesn't have any dependencies beyond the usual dependencies for building the wolfSSL library, so a compiler and a linker and whatnot, and the usual dependencies for building a kernel.
Okay. If you guys still have a further question, you guys can email us at facts@wolfssl.com. But thank you all for the insightful question, and thank you, Daniel, for hosting the informative webinar. And please don't forget to follow us on X at wolfSSL, as well as our LinkedIn and YouTube channel. And thank you again, and see you next week for post-quantum algorithm in Coral. Thank you.
Thank you, Shizuka.
Thank you, Daniel.
We have a question.
Oh, They have question. Okay.
How is wolfcrypt different from pcrypt module? Are we talking about wolfcrypt in general or the kernel module? I'm waiting for Pavan to answer live. Let's see if Shizuka, if I click on the answer live button, do you know what it will do? Oh, okay. So
Yes.
Pavan has clarified. He's talking about the kernel module. So wolfcrypt is a general cryptographic provider. wolfcrypt implements not just the entire FIPS140-3 crypto suite. It implements a wide variety of additional algorithms. We support the Chinese SM suite. We support a decent set of post-quantum algorithms, as I discussed, and many more algorithms besides outside the FIPS suite. The pcrypt module, I cannot recall off the top of my head which algorithms are supported by pcrypt and what role the pcrypt module plays. Do you have a particular algorithm or suite of algorithms or functionality that you're interested in hearing about, Pavan? While we wait for Pavan, I'm going to check on pcrypt, see what I can figure out. Oh, parallel encryption. Okay, so our implementations are fully parallelizable. That's a basic requirement for running inside the kernel. Is that there can't be any static data. We are fully thread safe, so we, in principle, are parallelizable. But that is a good question. I'm gonna please, Pavan, please open a ticket with us to ask about parallel encryption performance, and I'll get a more detailed response to you on that topic when you do. But the short answer to it is that we have to implement our cryptography and our crypto handles in a fully reentrant way just for compatibility with the LKC API. So we're already substantially parallelizable, and it depends on exactly how the Linux kernel is calling us.
Yes, if you have any technical question, please email us at support@wolfSSL.com. So and then we can assign to our engineer, and they can give you more technical answers. Yeah. And thank you so much, and see you next week.
Thank you again, Shizuka. Bye.
Bye.